I didn't get any special music for this video, so I'm just singing this song. Hello. Okay, today what I hope to do in this video is wrap up how to analyze the origin, the fixed point, of two-dimensional linear systems. Okay, we've already covered in previous videos when we have two real roots that are not equal to 0, that's in the blue, and complex roots, either with non-zero real part or 0 real part, that's in the green. Okay, we're going to handle several special cases here, which is going to let us prune off these last little edges. I definitely forgot to write the number 1 right there. Okay, great. So in our first example, what we're going to do is we're going to handle when we have a repeated root that doesn't happen to be equal to 0. Okay, that's the one we're going to handle first. Okay, after that, we're going to handle when we have two roots that are real, where one of them happens to be 0. Okay, and then as a final case, we'll discuss when we have a repeated root that is equal to 0. So all the eigenvalues are equal to 0. There's a couple special cases in here. We're going to have to handle everything in stride. We'll get there. It'll be fantastic. I promise. Okay, it's probably going to be crap. All right. First, I want us to consider this system right here. dx dt equals negative 2x plus y, and dy dt equals negative 2y. First, if you're faced with this, you should know that you can move forward and solve this explicitly without having to evoke any of this sort of matrix vector stuff. And that's great because it's going to give us an opportunity to kind of explore how would I tackle this. And the reason is because it's partially decoupled. The dy dt equation does not depend on x, so I can solve that. And as a matter of fact, my solution, y of t, is y sub 0, the initial condition, e to the minus 2t. Huzzah. Okay, you plug that in to the first equation there, and you wind up with the equation dx dt equals negative 2x plus y0 e to the minus 2t. You should recall how to do this basically with the method of educated guess. Okay, if you don't, review it. You get x of t equals, I've got it written down right there. Okay, cool. X sub 0 e to the minus 2t plus y sub 0 t e to the minus 2t. Okay, cool. I have a solution for x. I've got a solution for y. Fantastic. If I want to, I can write this in vector form. Make the y vector right here, which is equal to x, y. And so this will equal to x naught, y naught, e to the minus 2t. That is this term and this term in their respective locations, plus y naught 0 t e to the minus 2t. Cool, I have a solution. Now, the major questions that arise are the following. Okay, is this always the initial condition vector? That's the first one, and we'll cover that in just a second. Okay, is it always? The answer is yes. Okay. And then our second question would be, is this always y0, 0? The answer is no. Okay, if I look at y vector evaluated at the time 0, okay, then when I plug in 0 in here, this term vanishes. This term turns to 1. So if I did not know what this vector is, it would have to be my initial conditions. So yes, that is always my initial condition vector. Okay, what is this vector right here? Well, I'll give you a hint. It is your eigenvector for the eigenvalue negative 2. Okay, so let's see how we can extract that in a more general setting here. Okay, so while this is not the most general differential equation that will lead to a repeated eigenvalue, I think it's good enough for our purposes of just reusing the one we just had by writing it in matrix vector form. Okay, our step one is always find eigenvalues. And we do that by taking the determinant of -2 minus lambda, 1, 0, -2 minus lambda. That equals -2 minus lambda squared, and we need to set that equal to 0. And so this means that my eigenvalue, I zoomed out and zoomed way in. My eigenvalue is -2 twice. I have a repeated eigenvalue. Okay, fine. Let's find the eigenvector. My eigenvector in this case, okay, is going to equal -2 minus -2, 1, 0, -2 minus -2, multiplied by an unknown eigenvector defined, and we set that equal to the 0 vector. And what we've got is we've got 0, 1, 0, 0 times v1, v2 equals 0, 0. And we get the equations v2 equals 0 and 0 equals 0. Okay, that second equation right there, not helpful. Contains absolutely no information. This first one here does have information, that the second component of my eigenvector, in this case, should be 0. Now, what about the first one? Oh, it can be anything I want it to be. So the eigenvector that I'm going to go with is 1, 0. I could have gone with 38, 0, or why not 0? See what we did there? Okay. That's where it comes from. That's why it's also the eigenvector. All right. Now, you may be tempted to say, okay, great. I found an eigenvalue and an eigenvector. That means my solution is equivalent to that eigenvector times e to the minus 2t. Now, the problem is that can't be our general solution because it's not this linear combination in two different directions, right? This can't cover a plane. All this can do is trace along a line 1, 0. I can't fill in the rest of the trajectories. So how do we get that? Well, being motivated by this right here is that we always then will look for solutions of the form y0 e to the lambda t plus v t e to the lambda t. That's a lambda, that's a t, where lambda is my eigenvalue, v is the corresponding eigenvector, and y0 is our initial condition vector. Okay, you can plug this in, verify that it is a solution, and because each of these components right here are linearly independent from one another, you got it. Now, there's a small caveat in here. Okay, there is a situation where, what if y0 is already an eigenvector? Because it could be. Oh. Well, what's interesting there, if y0 is already an eigenvector, then v is either repeating the exact same information or is something completely different. It's the 0 vector. And we need to know how to deal with that, okay? But what that would mean, we can put this into a theorem. This is in the book, but I'm just writing it to bring our attention to it, okay? So suppose we've got a linear system of differential equations where A is 2 by 2 with repeated eigenvalue lambda. Okay, then our general solution is y0 e to the lambda t plus v t e to the lambda t, with y0 and v defined as we've got them right here. Okay, and we find v from this equation right here. If v is the 0 vector, okay, then what that means is that y0 is our eigenvector, and we have a straight line solution. which is very weird. Okay, it's a kind of it's an exasperatingly special case that you, generally speaking, won't run into, but it needs to be covered mathematically because it is an option. Okay, cool. That covers the first part of what if one of my eigenvalues is repeated. There we go. And not is zero. I almost said is zero. But there's another special case for that, because I didn't write down the most simple way to get repeated eigenvalues. That's the most simple way to get repeated eigenvalues, is when your matrix is diagonal or even upper triangular. But in this case right here, something goes awry. Okay, for this matrix, my eigenvalues are A, so lambda equals A. And then when I look at big A minus lambda I, and I multiply that by V1, V2, why, I get 0, 0, 0, 0 times V1, V2 needs to equal 0, 0. And so what this means to me is that every single vector is an eigenvector. Well, crap, what does that mean? Well, if I think about my xy plane, okay, what eigenvectors are supposed to do is serve as our straight line solutions to these things. Now, no matter where I put my straight lines, according to this, they are all solutions. Doesn't matter what angle I draw them at. Now, if A is positive, that just means in every single direction, I grow away from the origin. Okay, this is called an unstable star. If, let me go and draw another of these. If A is negative, then that means along every single direction that I draw, thank you to the student who taught me how to make straight lines on this program. I'm very happy about it. Boop. I crash in toward the origin, and this is called a stable star. Okay, this is the like special of special cases. Okay, it's very hard to arrive at these, but these are star nodes. Okay, this leads me to something I forgot to do. In the event that you have a repeated eigenvalue and you don't have every vector as an eigenvector. Okay, want to look at our solutions here. Okay, our solution, like we said before, is the initial condition, boop, boop, e to the lambda t, plus some eigenvector, t e to the lambda t. Okay, so how do I do this? Take our eigenvector here. Eigenvector is in red. Okay, so I know along my eigenvector, I need to be a straight line solution. Okay, let's go ahead and just assume that lambda is negative, sure. So that I'm crashing into the origin around there. Okay, now what this is telling me right here, this little bit that's extra, is that, well, e to the lambda t is still, lambda is negative, so that's still going to 0. But it goes to 0 from where? From the initial condition, because that's what's written right in front of that right there. Okay, but now we have this additional push-pull from this straight line solution. How to get that all geometrically? If I start anywhere, I come into the origin, and what's interesting here is that nobody is telling me to change the way that I'm curved, because there's not another straight line solution barring the way. Okay, I like to call these things pinwheels, but they're called degenerate nodes. And there's a reason I like to call them pinwheels. If we compare them to normal nodes, All right, so let's look at a normal nodal source. Okay, I don't know why I made my horizontal axis so tiny. Versus a degenerate pinwheel source. Okay, so this guy right here is going to have two separate eigenvalues, each of which has a different strength to them, right? Maybe one of them is pushing with like eigenvalue of 1, another one eigenvalue 10 or something like that. But what's important is that in both of these directions right here, I'm being repelled away. Red plus green makes brown. Okay, great. And we know that the game here is to figure out sort of which one's stronger as time goes on, and that tells us which way it bends. Okay? Now, this second situation here only has one eigenvector. Okay? Only one fundamental direction telling you which way it goes. And so everybody else just sort of, whoops, don't make a straight line there. I have a really hard time drawing these. They're kind of tough. Oh, why does it keep making a straight line now that I don't want it to? Oh, dear Lord. Undo. Just that guy right there. Okay, great. Whoop. All right. Pretend you're running your fingers along here in this circle, going clockwise. Okay, you'll always kind of be on the like outside of that curve. You'll always be going like, do I have anything curved here? No, I don't. That is so weird. Okay, but you always have a curve, and you'll always be going like this. Okay, where in the other situation, some of the time you'll be going like this, and other times you'll be going like that and hitting it. See, I'm moving with it, against it, with it, against it, with it, against it. Blow wind on this. This guy will spin. This guy will not. Pinwheel, not pinwheel. Degenerate node, node. Okay? So those are our differences. So we've got degenerate nodes and star nodes that can arise from the case, all the way back up here, that I have a repeated eigenvalue, okay, which is not equal to 0. So all that was that case right there. A lot of work. Let's now go for when I have two real eigenvalues, but one of them happens to be 0. Okay, this case is actually pretty straightforward to handle. All right, we have no reason to believe they're two distinct real. We know how to write down that solution. It always looks like this because these two guys are linearly independent from one another. But now we're in the case where lambda 1 equals 0 and lambda 2 does not equal 0. Okay, so my solution simplifies a little bit. Some vector plus some other vector e to the lambda 2t. Now I'd like for you for a second to imagine that lambda 2 is negative. Let t go to 0. Let t go to infinity. What's going to happen to this? This term right here vanishes, and all we're left with is this vector. Oh. Okay, let lambda 2 be positive. Right? Then as t goes to 0, I've got this vector plus that vector, sort of determining where I start, and then I build off from that. Interesting. Let's get our xy plane going on. Here's my y-axis. Here's my x-axis. Okay, let's get some colors going on, because colors are always nice to me. That one's going to be green. That one's going to be red. Green. Okay. Actually, no. Whoops, I want the red one. Okay. This is the easiest thing to draw, because we can go ahead, just like we've always done, which is say, there's a direction. Whoop. There we go. Where along this direction, I move according to lambda 2. Let's just suppose it's positive, just for grinsies. Actually, no, this is not what I want to do at all. I mess it up. whoops, come here. There we go. I want the green one first. Okay, whoops. This one is associated with the eigenvalue equals 0. Okay, lambda equals 0. Now, what that's telling me is that on there, if I start on this, I don't actually move anywhere on this straight line. So every single point on this line is an equilibrium. Right? Doesn't matter where you start. Now, if I start anywhere else, well, let's first find V2. No, in this direction, if lambda was negative, I could have drawn this. I don't know why I stopped. I like it oriented this way. I could have done it the other way. Okay, if I start on this red direction, I move in towards. Now, what happens if I start anywhere else? Well, what's going on? Nothing is changing with this component right here. The only thing that changes is that this component is, in this case, because lambda is negative, is trying to vanish. And so I'm going to move in the exact same direction as V2 until I get to that equilibrium point that lives on the line of equilibrium points. What if I go here? I'm going to move in that direction until I get to the equilibrium point that's on the line of equilibrium points. And it doesn't matter what I do there. So if one of your eigenvalues is 0, what that is telling me, and what that should be telling us, is that there is some, it's called a conservation law, okay? Because what this green line is telling me is that there is some intrinsic way that my two variables, x and y, combine to form stasis, okay? An example of this can be seen where if we just write down an equation that would have this character that I want. All right, let's say dx dt is negative 3x plus y, and dy dt is 3x minus y. What can you see about those two differential equations? I mean, namely, you should be able to see that dy dt is the exact same as negative dx dt. And what that tells me is that dx dt plus dy dt equals 0, which means there's a conservation law going on. Any change in x is mirrored by the exact opposite change in y, and vice versa, which means integrate this expression by time. X sub t plus y sub t is going to equal some constant, which means if I know x sub t and I subtract its value from c, then I will know y sub t, which means I don't need to know both variables. I just need to know one of them. There's redundant information. This is the hallmark of having one of your eigenvalues be 0, is that there's a conservation law, meaning there's some sort of redundancy built in, or some sort of constant that's there that never changes, some conservation, okay? And so you'll always get these sort of, these straight line, non-isolated equilibria situations, right? Which we've got right here. Cool. Now, what if both of your eigenvalues are 0? Okay, we got to think about that. That means the determinant of a minus lambda I, okay, is equal to lambda squared. Okay, that's what that means. Which means both of my diagonal elements, first off, have to be 0. Okay, reason being, like if we write down A, B, C, D, okay, that's my matrix A. Then A minus lambda I, the determinant of that is A minus lambda times D minus lambda minus BC. So far, so good. Okay, you might say, well, hey, AD and BC, they might cancel each other out. Well, that might be true, but you're going to have this negative A lambda and this negative D lambda there too. So I've got a lambda squared minus those two guys plus AD minus BC. Okay, so right here, what does this mean? If these guys are to vanish, this means D has to equal negative A. So far, so good. Okay. And then what this means is that this term right there is going to equal negative A squared. And that has to be the same as B times C. So maybe B is like A and C is like negative A. Well, I get something that looks like this. Let's say A, negative A, negative A. What are my eigenvalues? A minus lambda, negative A minus lambda, plus A squared. Okay, lambda squared minus A lambda plus A lambda minus A squared plus A squared. So lambda squared equals 0, lambda equals 0. Okay, now in this case, what's going on? We do have movement, but both of my eigenvalues are 0. I'm not going to worry about it. Basically, these sort of special cases are so oddball. Okay, try to find the eigenvector corresponding to A minus A minus A times V1 V2 equals 0 0, and you get A V1 plus A V2 equals 0. So maybe we can let V1 equal 1 over A. And so then I got 1 equals negative A V2. And so V2 equals negative 1 over A. And so I know that in that direction, which will look something like this, if A is positive, okay, I have no movement. Okay. That's weird. But I also know now that I can compute, oh, I don't have a second eigendirection. You basically don't have enough really to work with in this case, and you have to resort to looking at things a little differently. Namely, what I would be looking at here is dx dt plus dy dt, right, which equals 0, which we should get from looking over there. Okay, and so again, x is going to equal some constant minus y, plugging that in, and you get some very simple things. Essentially, the way that when you have two zero eigenvalues, either the way you have things written down is just way over convoluted for a much simpler example, or every single point is a fixed point, which is dumb. Okay, that's going to end this video. I'm going to do another video right now, which is going to be showing us basically how to take all this stuff, put it together, so that we can make all this a lot easier without needing to redo it all the time. It's by basically analyzing the trace determinant plane. Okay, I'm gonna push the button down here now. Stop recording.